Wind that normally keeps weather systems moving briskly across entire continents keep getting stuck in huge, slow-moving loops that trap the same weather over the same region for a week or more at a time. This summer alone, that exact stuck pattern has already produced 2 separate record-breaking heat domes over North America within about 3 weeks of each other, an event forecasters are calling genuinely unusual. Similar blocking patterns have simultaneously driven a second dangerous heat dome across parts of Western Europe this July, suggesting whatever is happening isn't confined to a single continent. So let's actually investigate what the jet stream is doing right now and why it keeps getting stuck this way. To understand the investigation, you first need to understand what the jet stream normally does when it's working the way it's supposed to. It's a narrow ribbon of extremely fast wind, typically found around 30,000 to 39,000 feet up, right where commercial jets often cruise. It forms because of the sharp temperature difference between cold polar air and warmer air to the south, and that temperature contrast is what gives it its speed in its west to east direction. When the jet stream is strong and relatively straight, weather systems move through in a predictable, orderly rhythm, which is exactly why a normal heat wave typically lasts only 2 to 4 days before it gets pushed along. There are actually 2 separate jet streams in each hemisphere worth knowing about, the polar jet and the subtropical jet, and they behave differently depending on the season. In summer, the polar jet naturally retreats northward and weakens somewhat as the polar regions warm relative to winter, which is part of why blocking patterns tend to show up more during the warmer months in the first place. That seasonal weakening isn't itself the anomaly researchers are investigating, but it does create the baseline conditions that make summer blocking more likely to occur than in the depths of winter. The first real clue in this investigation comes from what happens when that temperature contrast weakens. Rather than flowing in a straight line, the jet stream naturally develops ridges and troughs called Rossby waves, and how large those waves get is directly tied to how sharp the difference is between polar and mid-latitude temperatures. When the A contrast is strong, the waves stay relatively small and the jet moves quickly along its path. When the contrast shrinks, the waves can grow large enough that a ridge of high pressure gets essentially cut off from the main flow, stalling in place instead of continuing to move, which is exactly the mechanism behind the blocking patterns responsible for this summer's back-to-back heat domes. The second clue researchers pursued was an obvious suspect, the Arctic. The Arctic has been warming significantly faster than the rest of the planet for decades, a phenomenon called Arctic amplification. And for years, the leading hypothesis was straightforward. If the Arctic warms faster than the mid-latitudes, the temperature contrast that drives the jet stream shrinks, and a weaker jet stream should wobble into bigger, slower waves more often. Several influential studies through the 2010s found evidence supporting exactly that link, showing what looked like a genuine increase in jet stream waviness tracking, alongside the accelerating Arctic warming. That hypothesis was intuitive enough that it spread quickly beyond scientific journals and into mainstream weather coverage, becoming something close to conventional wisdom for explaining almost any unusual blocking event. It's easy to see why the explanation caught on so widely, since it offered a single, satisfying cause for a genuinely confusing pattern of extreme weather showing up across multiple continents at once. Here's where the investigation takes a turn that a lot of headlines skip over entirely. Not every research group found the same result. A widely cited study out of the University of Exeter specifically tested whether Arctic warming was actually driving the wavier jet stream pattern, and found that it wasn't, at least not in the direct causal way earlier research had assumed. That team argued the apparent link was more likely a case of natural jet stream fluctuations influencing Arctic temperatures, rather than the other way around, essentially flipping the assumed direction of cause and effect. Layer 3 of this investigation adds even more nuance. Long-term observational records show that the noticeably wavy jet stream pattern researchers were tracking through the early 2010s didn't actually continue consistently through the rest of that decade. By the early 2020s, some researchers concluded the apparent increase in waviness during that earlier window might have simply been natural variability, a temporary wobble, rather than a genuine long-term climate trend. It's worth stressing that this disagreement wasn't between climate scientists and skeptics of global warming, since every researcher involved in the debate accepted the broader evidence for both climate change and Arctic amplification. Without question, the disagreement was narrower and more technical, focused specifically on whether that warming translates into a measurably wavier jet stream, which is a much more specific and harder claim to prove than the underlying warming trend itself. That doesn't mean Arctic amplification isn't real, since the warming itself is extremely well documented. It means the specific claim that Arctic warming directly makes the jet stream wavier turned out to be far less settled than it initially appeared. Layer 4 comes from a completely different direction that researchers weren't originally expecting. A more recent analysis pointed instead toward the tropical Pacific as a major driver of increased summertime jet stream waviness rather than the Arctic. That research found that cooling sea surface temperatures over the tropical eastern Pacific have suppressed convection along a band called the intertropical convergence zone, and that suppression generates its own wave pattern that propagates directly into the jet stream's path. The researchers behind that study explicitly stated, their findings suggest a smaller role for Arctic amplification in mid-latitude wave behavior than earlier estimates assumed, shifting a meaningful share of the explanation toward the tropics instead of the poles. This is a genuinely important moment in the investigation because it shows two completely different parts of the planet, one at the pole and one at the equator, both producing plausible mechanisms for the same wavy jet stream behavior. Rather than one clean answer, researchers are increasingly finding that multiple systems can push the jet stream toward the same kind of stuck, blocked pattern, which makes isolating a single dominant cause considerably harder than early 2010s research assumed it would be. Here's a related thread worth mentioning as an additional layer, without overstating the connection. Separate ongoing research into the Atlantic meridional overturning circulation, the deep ocean current system that moves warm water northward through the Atlantic, has also found measurable weakening in recent years, based on direct seafloor measurements taken across multiple decades, because that circulation helps regulate the very temperature gradients that drive atmospheric circulation patterns in the first place. Some researchers see a plausible, if still unconfirmed, link between a slowing ocean engine and a more sluggish, wavier atmospheric one operating above it. This connection remains an active area of study rather than an established fact, and no research group has yet demonstrated a direct causal chain between the two systems with high confidence. Now, for the genuinely speculative piece of this investigation, which I want to flag clearly, a small number of researchers have proposed that, as both Arctic warming and ocean, circulation changes continue over the coming decades, blocking events like the omega blocks behind this summer's heat. Domes could become measurably more frequent or persistent, compounding on top of each other in ways current models don't fully capture yet. This remains speculative and is explicitly described by the researchers themselves as an area requiring significantly more data before any firm conclusion can be drawn, particularly given how much disagreement already exists over the mechanisms driving current behavior. If investigations like this, the kind that actually walk through the scientific disagreement instead of flattening it into a single scary headline, are useful to you, like and subscribe, because this channel breaks down exactly this kind of layered climate research regularly. Zooming out, here's the bigger pattern this investigation actually reveals. The jet stream isn't simply breaking in some permanent, one-directional way, and no credible research group is claiming that it is. What the accumulated evidence increasingly points toward is a jet stream influenced by multiple, sometimes competing pressures at once, from Arctic amplification to tropical Pacific. Convection changes to possible ocean circulation shifts, all interacting in ways scientists are still actively working to disentangle. The specific back-to-back blocking pattern behind this summer's two major heat domes fits comfortably within that broader picture of a more complex, less predictable atmospheric system, even without requiring a single definitive cause to explain it. It's also worth being honest about what this uncertainty means practically. Forecasters can identify when a blocking pattern like an omega block has formed and track it day by day with real confidence, since that's a direct observation rather than a prediction about long-term causes. What remains genuinely uncertain is how often patterns like this will recur in future summers. And that's exactly the kind of long-range question this ongoing scientific debate is trying to answer. Distinguishing between what forecasters know with confidence today and what climate researchers are still actively debating about tomorrow is one of the most useful habits a viewer can build when following stories like this one. So what can you actually do with an investigation like this one? Treat any extended blocking pattern, whether it's called an omega block or simply described as a stuck weather pattern in your local forecast, as a signal to plan several days ahead rather than assuming normal short-term variability will bring relief on the usual 2 to 4 day schedule. If your region has experienced one of these prolonged patterns already this year, build simple redundancy into your routine, like a backup cooling plan or a flexible outdoor schedule, since the research increasingly suggests these stuck patterns aren't necessarily rare anomalies anymore. This matters just as much for cold season blocking as it does for summer heat, since the same underlying mechanism can trap frigid air in place for extended stretches during winter rather than warm air during summer. If you live somewhere prone to either extreme depending on the season, it's worth getting familiar with how your local forecast office specifically labels blocking patterns, since that terminology is often your earliest practical warning that a multi-day event is forming rather than a routine short-term system. Follow your National Weather Service's medium range forecast discussions rather than only the daily forecast, since those discussions often explicitly mention when meteorologists are watching for a developing block days before it fully forms. That extra lead time is often the most practical benefit available right now, even while the deeper scientific debate over exactly why these patterns are forming continues to play out among researchers. Here's the honest summary of where this investigation currently stands. The jet stream depends on the temperature contrast between the poles and the tropics, and when that contrast weakens or gets disrupted, the resulting waves can grow large enough to stall entire weather patterns in place for a week or more. Early research pointed heavily toward Arctic amplification as the driving cause, but more recent work has both challenged that direct link and introduced a competing explanation centered on the tropical Pacific instead, while a possible connection to a slowing Atlantic circulation remains an open, unconfirmed thread. No single cause has been definitively established or and scientists are refreshingly candid about that uncertainty rather than forcing a tidy conclusion the data doesn't yet support. The IT kind of honesty is worth valuing rather than dismissing, since a genuinely complex atmospheric system rarely reduces cleanly to one simple headline explanation, however satisfying that explanation might feel in the moment. If clear, honest science breakdowns like this are useful to you, subscribe so you don't miss the next one, because this exact research area is moving fast, and new findings are being published regularly. Stay curious, keep watching the sky, and I'll be back the moment there's real movement in this investigation.